Hello, everyone. My name is Sebastian Diaz, and I am one of the colleagues of Allin-Wayra. I'll spend just a few minutes giving a brief intro about this initiative before handing over to John. Um, what is Allin-Wayra? Allin-Wayra is a global initiative under IGAC, the International Global Atmospheric Chemistry Project. Our activities is focused on small sensors, also called sometimes low-cost sensors. We don't like that name, but everyone knows it through that name. Our name, Allin-Wayra, comes from Quechua, a Latin American pre-Columbian language, and can be understood as good air or winds of change, which it's trying to reflect both our scientific focus and our broader mission. At its core, Allin-Wayra is about building a diverse and inclusive community of practice around small sensors with particular focus on regions like in air quality measurements. We really believe sensors can help us to advance through collaborative initiatives that build capacity and promote that accessibility. Um, this is our team. We are led by a small coordinating team, but it is very much into the community. You will see many places are represented there. Of course, we are always looking towards having more representation from different areas. Um, I will let there a few links and our email address for people in case wants to reach out and get into contact. If you want to sign up for our mailing list, just scan that QR code. Uh, if you're interested, please feel free to join, to reach out. As I said before, we are organizing an EGU session, which is called Low Cost Air Quality Sensors, Challenges, Opportunities, and Collaborative Strategies across the world. And you can scan the QR code to see what we are waiting for from that session, from that specific session. And now I will hand it over to John, who will introduce today's topics and our speakers, Brian, Stacey, and Valerio Ferracci. John, floor is yours.
Yes, thank you very much. We all understand that there's a need for low-cost sensors, LCS, just due to the financial issues of monitoring air quality everywhere. And the problem is, how do we ensure that they produce the data quality we require? And the answer is standards. And we have been working, Valerio and Brian and I and many others, we have all been working for quite a few years on establishing standards for low-cost sensors. And both of these two, Valerio and Brian, are both operating and continue to work in the area of being coordinators for standards. And I'd like them to tell us where we can go. Now, you're probably worried that we won't produce sensors that meet the data quality you require, but that's unreasonable. You must consider that we really can. It just requires really careful validation and work behind the curtains. And I'd like both Valerio and Brian to tell us about that. Who's going first? Brian, are you going first?
No, Valerio's got the slides, so he's going to say hello to start.
Valerio, you're running the slides.
Brilliant. Let me share my screen. Can you all see it in the full screen mode?
Yes, that's all good.
Fantastic. Right, let's get started.
Good. Thank you.
Okay. Well, thanks, Seba and John, for the introduction, and guess good morning or good afternoon or evening, depending on where you are on the planet. So today, for the next 30 minutes or so, myself and Brian will tell you all about standardization and air quality, going from the reference methods to these new sensor technologies. So here's a brief summary of the points that we will cover. So why do we care about standardization? Why is it important? What are the bodies that actually do the standardization work? And then how do these standards affect you, the end users? We'll give you a few examples of standardization in action through the years. And then we'll move on to the new frontier of what we're doing in terms of standardizing sensor systems for equality before drawing some conclusions and sharing some thoughts about what lies ahead in the future. So, why is standardization important? There's a series of bullets that tell you why, but really it's to ensuring that the data you collect are harmonized and comparable. So what we may measure in London or in the UK can be compared to something measured on the other side of the world, be it, I don't know, Chile or even Antarctica. And really, we need guidance and standardized test procedures to evaluate, in the case of air quality, instrumentation and analyzers, to set out methodologies for calibration so that at every air quality monitoring site, these are carried out in the same way. Provide details on how these instruments are installed, what quality assurance and quality control measures you might take to ensure that your data is of high quality. And really, standardization, you can think of it as a foundational framework that really underpins really the world as we know it today. And it'd be interesting to carry out some sort of thought experiment. So what would the world look like if standardization was not in place? And this is some colleagues from MPL. Richard Brown-Paul Brewer wrote an opinion piece recently on what would a world without metrology look like. So the science of measurement. But metrology really underpins standardization, so we can adopt some of their ideas and apply them to standardization. So in a world without standardization, science would be less rigorous, less reproducible. So try and weight things on an uncalibrated balance. Or I'm a chemist by trade, so try mixing in, I don't know, volumes of a solution without calibrated pipettes. As a result of science being less robust, the trust in science and experts will be weakened. And then all the decisions that taken based on scientific evidence would also be weaker. And the decisions themselves would be poorer. And ultimately, all the kind of trade and industry would be less effective and efficient. So there'd be more waste, be more expensive, and there could be critical failures in the supply chain. So we need standardization. And now in the next section, we'll look at how standards are produced and who is behind the bodies that actually carry out the standardization. So over to you, Brian.
Thank you, Valerio. So we're both involved in a pair of international standardization organizations. One's a European-based organization called CEN, which is based in Brussels. It's a European standardization, European Community for Standardization, I'm sorry, which builds standard methods for use in Europe. And that involves a group of technical experts working on working groups to agree consensus for how we build the standard methods. It's fair to point out at this moment in time that most of the people that work on those working groups are doing it on a voluntary basis. with very little in the way of funding from their institutes that they work for. Typically, he said, with no bias or bad feeling about it at all. But we work towards a common goal to work in a direction of travel that improves our measurement technologies. And overarching on top of that is the International Organization for Standardization, which works in a similar way to the European working groups, but has a more global reach than CEN, although the two organizations do work quite closely together in terms of working towards common goals. So where there is genuine benefit in having a single standard method that is beneficial to everyone, then one standard method is developed. Moving on, please, Valerio.
Brian, can I just add that for the North Americans, the ASTM is ANSI are quite critical as well.
Okay. Thank you, John. Okay, so next then, Valerio, please. So having standards is great, but how does that affect end use, people that want to use these products? So the standards describe a number of key objectives to basically work out what the method we're going to use is going to be, because there may be multiple techniques that are available for making measurements of, say, for example, nitrogen dioxide, or for particulate matter. So to have a standard method is really important to make sure that everyone is able to compare their data with everybody else. The standards set out a series of performance requirements to make sure, for example, that if you introduce a concentration of gas to an analyzer, you get a response. If you double that concentration, do you get double the response from the analyzer? Those sorts of things like linearity, the accuracy of the method, whether or not the method is subject to things like interferences, like temperature and pressure and humidity and other gases, for example, or have to have sets of limits applied to them to make sure that those don't contribute significantly to the uncertainty budget of that method. And from there, it also allows you to evaluate the uncertainty of the method you're being used and the methodology that you apply to your calibration techniques. It also allows you to independently verify the performance of your instrument. So you can take, if you're a manufacturer, you can take your device to an independent test house to do all of those tests for you, to evaluate it, provide an uncertainty calculation and a certificate that demonstrates that your method actually is fit for purpose. And also it provides guidance for end users to say, this is how you install it, this is how you operate it, and these are the sorts of things that you need to think about when you're running that instrument on a long-term basis. Most importantly, it means that as an end user, you can go out and you can buy a measurement device that has gone through that testing process and has a certificate applied to it, and know that out of the box, it's going to work in a way that you expect or need it to. And provided that you operate that instrument in the way that is specified or directed in the standard method, your instrument's data that you get from it should be fit for purpose. And the should is in italics, and that's important because there are things that may or may not happen in the field when you're operating it that may have an impact on data quality. So you just need to keep that in mind. And the next slide, please. Next slide, Valerio. There you. Sorry, thank you.
Sorry.
I'm patient. So we've been doing this for a while in terms of in looking at developing standard methods, and I just wanted to kind of take you on a journey for how that has worked in the real world of using very high quality reference grade instruments. So back when I started working in 1989-ish, we didn't have any kind of methodology for comparing measurements that were made in the UK to comparing measurements that were made in France or Germany or Belgium or Italy or anywhere, you know, and wider afield for places like Japan and North America, there was no way of making sure that measurements we made were directly comparable to measurements that were made everywhere else. And in 1991, the European Union decided that that wasn't acceptable. We needed to understand the metrology of what people were doing, and harmonize and establish a traceability chain between different member states across Europe. So they built an intercomparison exercise that you can see in the picture here. There are a number of candidates from different member states across Europe that are all sampling the same gas from a manifold delivery system and reporting on what they believe the concentrations of the gases in the sample manifold were. You report that, you compare it against what everyone else is doing, and you get an idea of how close you are both to the real number and also across all of the participants in the exercise. And you can see that there are, well, you can't see, but there are loads of people that are wandering around this laboratory looking at everybody else's instruments and saying, wow, what do you get? Do you get 35? So it kind of helped in understanding what everybody else did, and pulling in a common direction. So when we first started out doing this, there were a large number of participants or measurements that had poor agreement both with each other and the test gas concentrations that were introduced to all the instruments. But by implementing standard methods and by sharing knowledge and exchanging information, everybody improved on their measurement processes. And by this year, very few measurements now show poor agreement, and that's more to do with instrument faults rather than actually measurement errors. So everyone's been on a journey, and now you can turn up at an intercomparison exercise and be pretty sure that what you measure is basically what everybody else measures. And that's worked really well for gases. For PM, it's much more difficult because you can't introduce calibration gases or calibration mixtures of standard particle concentrations easily to PM analyzers. So you have to run them side by side in an environment where you've got lots of PM around and then compare measurements at that point. But the test program for that is similarly successful. So the standardization as a philosophy works really well in this kind of world. Next slide, please, Valerio. So this is a picture of the PM samplers that are set and undertaken in northern Italy in the winter when concentrations are really high in North Italy. But the point I'm trying to make in here is that the standard methods evolve over time. You can't just write a method and then walk away and hope that it's going to be valid in 20 years' time. These things change and evolve as our knowledge of what's going on in the atmosphere and the measurement techniques improve. So this is a journey that for PM started way back in 1995 when the method was first designed and built and then published in 1998. But it was realized quite quickly that the method wasn't fit for purpose in terms of the sampling techniques that were used, the filter materials that were used, the conditioning in the laboratory for the weighing and pre-weighing and post-weighing of filters, all had to were subject to some significant modification. And in 2005, the PM 2.5 method was published. And even then, still both were acknowledged to have lots of shortcomings associated with the collection of filter material, collection of particles on filter materials. So we went straight back into the method development and built a much more robust set of standard methods. So in 2014, that was republished. So you can see that's 9 years later. I think the point is that getting consensus across everyone to work towards a common standard is quite difficult. And in that time, lots of further evidence emerges that makes it really difficult to make the standard method current. So PM, the standard method is gravimetry. So you collect material on a filter and then pre and post weigh it, and that's your concentration over a daily average. But that's not really very helpful if you want to measure in near real time to alert people to pollution episodes. So a method for demonstrating equivalence was devised in 2017 that allows direct comparisons with automatic analyzers and gravimetric methods. Again, that's not ideal. It's not perfect. So there have been continuous processes to update the reference method and also to update the demonstration of equivalence method. So it carries on all the time. So 30 years on from when we first started on this journey for PM, we're still going and improving and enhancing all the time. Okay, next slide, please, Valerio. I think that's you, isn't it?
Yeah. So thanks, Brian. So as Brian, as you can gather from the previous slide, it can take many years to draft a standard, and this is down to a variety of reasons. So again, there's a lot of evidence that needs to be collected and evaluated. So this could be from inter-comparison exercises that Brian describes, peer-reviewed literature, reports, etc. Once you've evaluated the evidence, then the experts or the different representatives on the working groups need to agree on what's written in the draft standard. And eventually the draft goes out for review. So all the standardization bodies in each country go through the draft. They have some questions and comments. And you can think of it like a peer review process when you submit your manuscript for publication. So when the working group gets the comments back, they need to be addressed, and only then the standard can be published. So as you can see, this is probably the reason why it takes so long to get to produce standards or even update them in the case of existing standards. But it's not all about. It's not only about standards. There are other standardization documents that can be produced in the absence or before a standard materializes. And these are the technical specifications or TSs and the publicly available specification or PAS. And generally, these are represent the direction of travel towards the standard. So they deal with best practice for end users or validation steps to make sure your data is of the best possible quality. And in most cases, they are the first step towards a standard. So they normally apply to emerging technologies. So it might take, as we saw, years to get to a standard. But in the meantime, in that void between the technology being used and the standard, we can provide some guidance through these documents. And this is pretty much what has happened for sensor systems in air quality. So it's you, Brian. Oh, no, you're on mute. Sorry.
Brian, you there?
Yep, sorry, I'm muted. I was rabbiting on there and not realizing I was talking to myself. I'm sorry. Yeah, there are lots and lots of opportunities for using air quality sensors that don't necessarily exist in the same way for reference grade equipment. So I suppose the most important one is that these things are significantly cheaper to buy than a reference grade analyzer. So an analyzer that measures NOx is probably in the region of $15,000, and you can buy a whole bunch of sensors that would not touch the size of $15,000. So it's relatively cheap to buy really quite useful measurement data from low-cost sensors. And you can also measure in very high time resolution. You can do that with reference analyzers, but 1 minute data is really easy for low-cost sensors. because they're cheaper, you can get lots of really useful spatial distribution information. So you can cover a very large area with lots of monitoring sensors for not significant outlay, and that gives you really good information about looking at hotspot information to work out where the pollution sources are. They're usually low power, which lends itself to maybe using solar panels and backup batteries to run them where you don't have access to power. And I've put a question mark on this. You can put them out, turn them on, and walk away and just get data, he said, hopefully. The downsides to low-cost sensors is that they're not all the same. So if you buy from manufacturer one, and then buy a similar system from manufacturer two, they will have different methods for turning what comes out of the sensor into what they call concentration units. They will all have sensitivities to the location type that they're in, the temperature, the humidity. They will be subject to interferences from different species, gases. Summer and winter might very well give you different results. If you put 100 side by side, you may not get the same number from all of them. So repeatabilities can be quite an issue. And really, in some ways, you probably need to think about whether or not you can actually plug them in, turn them on, and walk away. There are lots. It's almost at the moment the same level of effort after turning it on and starting to collect data as running a reference grade monitoring station. So you just need to kind of bear that in mind when you're thinking about what you want to buy. Okay, so I think that probably segues nicely into Valerio.
Thanks, Brian. So what have we been doing about these sensors? How do we address these challenges so that we can make the most of the opportunities? So these are the two documents that we're going to talk about for the rest of today. There is a technical specification from CEN Working Group 42, Part 1 and Part 2 on sensor systems, and the PAS 4023 as a code of practice for the use of local sensors. And the key really here is that these documents do not dictate what you must do, but it's guidance to how to use the systems and how to obtain the best quality data out of them. So let's start from the technical specification. So it's divided in two parts, Part 1 and Part 2. One focuses on gas air quality sensors, and Part 2 on particulate matter. So they describe a series of tests to evaluate your sensor system. So in the case of the gas sensors, there is a laboratory component, so a series of laboratory tests under controlled conditions where you try to establish the response time, linearity, and repeatability of the sensor systems for two different pollutants. And then a field element to the evaluation. So co-location with the reference instrumentation, so normally at an air quality site or a super site, and then evaluating the sensors against the reference. For Part 2, for particulate matter, it's slightly different. So the vast majority of the evaluation is carried out in the field. So we have these extended field collocation with the reference, but there is a smaller, but there is still a lab component to the evaluation, which mainly targets just coarse particulate matter. So the particles with diameter between 2.5 and 10 micrometers. Now, once you carry out all these tests, the TS is a series of equations to help you calculate the total uncertainty in your sensor system for a particular pollutant. And based on that, the sensor is then assigned a class, either 1, 2, or 3, with 1 being the highest quality. And this is based on the total uncertainty. So this is a table from part 2 for particulate matter. And you can see here the DQO. So this is the data quality objective. So the bands, if you will, of the uncertainty. So for a class 1 sensor, your total uncertainty has to be below, in this case, 25 micrograms per meter cubed, or about 50% of the limit value, or 15 micrograms for PM2.5, and so on. And there's similar values and tables for the gas sensors. And here's an example of, in this case, for part 1, so the gas sensors, of a flow diagram that describes all the different tests. So you start with a series of preliminary tests that address these main variables for your sensors. And then you carry on into either further laboratory tests, looking at things like drift, long-term drift and interferences, or with some short field deployments, or alternatively, you can go down the route of extended field tests. But ultimately, you look at the performance of your sensors in terms of uncertainty and data quality objectives, and then they get assigned a class. So for the laboratory tests, you do need dedicated facilities. So really, we're talking about exposure chambers, and you need to ensure that you control the environment very tightly. So an example of this is a facility that we have at NPL, the National Physical Laboratory in the UK, which is the Multiple Atmosphere Controlled Environment, or MACE for short. And you see here in the pictures, this is a series of exposure chambers. We have 6 of them, and each one can accommodate a sensor system, as you can see pictured here. We control the temperature using an environmental chamber. We control the humidity that goes into these exposure chambers, and obviously the composition of the air. So if we're testing for, say, nitrogen dioxide, we can vary the concentration inside the pod. But we also constantly monitor what is inside these chambers. So you can just about see here, this is the tip of a hygrometer probe that sticks out into the chamber. So we know what humidity we're putting in, but we're always double checking that it is what we think it is. And similarly for the target pollutants, we can also sample air from inside the chambers into a reference analyzer. And here's an example of the preliminary tests for carbon monoxide, in this case, CO. You can see, let's start from the simple things. These very flat lines at the bottom, these are all your environmental parameters from the chamber, so relative humidity, temperature, and pressure. As you would hope, we control the environment, and they're reasonably, they're very stable. In red, you have the reference analyzer. So this would be the non-dispersive infrared for CO. And then in different shades of green, you have 3 sensor systems. And you can see a series of tests. So from 0 to a span concentration. Here, for example, we evaluate the response time. In this section here, the linearity, and here the repeatability. So this is one component of the tests. The other component would be the field work, and I'll pass on to Brian for this.
Yeah, thanks, Valerio. I'm conscious of time, so I'm going to quickly skip through this. So it's really important to understand how the sensor systems work in the real world as well as under the controlled laboratory conditions. So you co-locate them side by side with reference monitoring stations, and you see there's a selection of different sensors here. We don't currently do this extensively in the UK, but mostly for interest and for specific projects where you're trying to deploy sensors into targeted locations. The 2 animations kind of give you an idea of the variability on a month-to-month basis that we found on NO2 and PM10 measurements. This is really early days, so 2019 to 2021, and a rolling monthly mean, and you can see that the scatter plots look quite scary when you go through from winter to summer. I'm not saying that that's what happens now, but that's certainly what happened in the early days, and it's something that if you have access to a reference grade monitoring station, putting out sensors to look at the relationship on a co-location basis is a really valuable, important thing to do. Valerio, back to you.
Okay, thanks, Brian. And again, yeah, you're right. It's getting late. I'll go very quickly through this. This is the second document that we were going to touch on, which is the PAS. So a publicly available specification. This is was developed in the UK, collaboration with the British Standardisation Institute, and really it's different from the technical specifications. It's more of a guidance for end users, and is aimed at a variety of a very varied audience, from local authorities to citizen scientists. It's for outdoor deployments only, and you can download it for free if you follow the link from this QR code from the BSI website. Now, very briefly, the PAS takes you through all the steps to planning and actually carrying out a measurement campaign. So from actually selecting sensors that are fit for purpose to where you actually place them during the deployment. So to make sure that the air you're sampling is truly representative of outdoor air and doesn't suffer from effects like stagnation, like in this example on the right. But then after you've collected your data, there's a large part of the PAS talks you through what you can do with the data to ensure that it's of the highest quality possible. So very briefly, there's not a one-size-fits-all approach for the PAS. So depending on your scenario, so whether it's a short citizen science project or a more complex long-term monitoring campaign, you may have to do different measures. So for citizen scientists, you might just want to establish whether a pollutant is present or not. Don't really care about perhaps drift or comparability. For intervention, so if you introduce, say, a low traffic zone or you want to detect a hotspot, you might need to take measurements before and after intervention. So you might start looking into temporal drift and behaviors. You might want to deploy multiple sensors across an area. So you might want to look into inter-system variability. And obviously, when we go down to the right, we have more complex situations, almost verging onto the reference monitoring. So we have long-term monitoring. So you really need to look at things like drift and interference. So for each one of these scenarios, there's a series of recommendations and steps that a user can take, say, for example, on selectivity, comparability, drift, and interfering variables. But obviously, as you move from the left to the right, the amount of stuff that you as an end user need to do increases. So, conclusions. I think we all agree that local sensors have a great potential to effectively revolutionize air quality monitoring. We talked you through the initial steps that we're taking towards standardizing these systems for air quality monitoring. The CEN, especially the working group, the work of Working Group 42, has led on the technical specifications for gas and PM sensors. And in the UK, we have the PAS that's been currently adopted by local authorities across the country. And over to Brian.
Okay, thanks, Valeria. If you just just go through them all now to get to the end. I think I would say in conclusion that there are no single right ways to undertake monitoring with low-cost sensors. I think that the key point is really to make sure that what you do is fit for purpose. There's lots of ongoing work to try and provide validation methodologies and evaluate sensor systems against the technical specifications, which will eventually become full standard methods. QAQC is really important, but you can do really clever things. So this plot here really is looking at how you can reduce your own personal exposure by choosing a different route to walk. So if you walk along the road, you might expose yourself to very large concentrations of nitrogen dioxide or PM. If you choose to get from point A to point B, so from top left to bottom right, if you choose a quieter route, then you can drastically reduce the amount of pollution that you're exposed to. And this is the sort of thing that you can demonstrate really clearly with low-cost sensors. So there's no limitation really to the applications that you could apply low-cost sensors to. And I think the key is that we need to make sure that the standard methods and the technical specifications that we work on allow us to exploit the advantages that sensor systems can provide us. That's it, I think, Valerio.
Thanks, Ryan. Just a final slide. You can download the pass from the QR code, some contacts there, and thank you for listening. And we can answer any questions now.
Yeah. Thank you, both of you. A few comments. First of all, the idea that the 17660 came out of as a first step. Brian, you and I know that took us 5 years to come up with that first step. It was not a simple first step. So 17660 was an incredibly huge amount of work from a lot of us working for so many years to achieve it. And what one advantage I'd like to remind people of, that when you talking about low-cost sensors, when they're a network, we're developing technologies that allow us to calibrate the entire network together and use that advantage of the network. And I'm sure you both agree with that. That's quite an important point, that individually they're tough to calibrate, but when they're in a network, we have methodologies that allow us to get much better data quality than we would expect from a single unit. And you both pointed out something that is fundamental, that laboratory to field is always a difficult topic. And I'd just like to say that it's seasonal and climatic problems of when you move these sensors from the lab out into all of our globe, whether it's tropical, whatever different areas, we have to learn to adapt to those different climates and seasons. And just the most useful thing I find from these low-cost sensors is source apportionment. It's very, very simple. If they may have an offset error, you can still use them to locate specific hotspots, which you both talked about, which I think is really, really useful. And finally, I just state that we're talking about CEN and ISO, but just want to remind people that there are also the Japanese, the Chinese, and the North American standards, CSA, ASTM, ANSI, so we're all trying to unify ourselves on our standards to try to have a more global attitude. That, and the most important point is, if a researcher is going to test a sensor, look at the standards and try to use the procedures and the processes in those standards so that your results can be compared with other people's. We need questions.
If I could quickly come back at you, John. Yeah, it took ages for the development of the technical specifications within CEN. And I think it's fair to point out that there are a significant number of widely varying opinions about the right way forward. And that was one of the major problems with building the technical specifications. So and that's just for testing a single sensor, you know, and I agree that there's so much that can be done to look at the actual data sets from networks, and I know Rod's on the call, that we can employ to enhance. But I guess the challenge with that is that if we had 16 different opinions within a group of 12 people for testing instruments, we're going to have loads and loads of different feelings about how to move things forward for machine learning or artificial intelligence, or however we choose to apply algorithms to measurement data. So it's not going to be a quick process to build a specification for that kind of technology, I think, personally.
Yeah. Let's go to. We have.
Sorry,
Q&A.
John. Sorry,
we got to handle Q&As.
we need to go to the questions, to the Q&A. We have 12 minutes now. So in order to accomplish that, one thing Federico Dallo is asking if we are going to share the slides. We will confirm that to you later, Federico. We need to see if Valerio and Brian are happy to do that. The next question from Luca Schindler, he says, when you refer to laboratory tests of low-cost air quality sensors, do these refer to the characterization of the sensing element itself, or to the sensing platform, electronics, housing, air inlet, firmware, data processing, etc.? The same sensors can be housed in different platforms. I don't know if you, Valerio, or Brian want to take that.
So the way it's specified in the TSs, it's the whole platform. So it's the whole pod, or whichever you're going to call it. So including the enclosure, the inlet, the electronics, and yeah, even the algorithms it uses. So obviously it's a black box as far as the TS is concerned, but it's the whole thing that is tested. Obviously, separately, you could repeat those sequences of tests for we can test things that are very early technology readiness level, if you will, but that's separate. In terms of, for this context, it's the whole thing.
We're quite careful about separating the phrase sensor and sensor system. Yeah. And that's something in 17660 we were very careful about. So the question is, yes, we test the sensor system, not the sensor. Are you happy with that, Valerio?
Very.
Yep.
Thanks, John.
Thank you, guys. The next question also from Luca. Can low-cost air quality sensors platforms be reliably used in indoor environments? What do you think?
I've got to answer that one. I'm working on IAQ, IEQ. That's what I'm working on at the moment. And yes, IAQ, IEQ focuses more on VOCs, volatile organics, and we're more concerned about air ventilation, whereas outdoor air is more focused on some of the particles, but mainly the inorganic gases. So they're different requirements, but they both should. And IAQ is far behind outdoor air in terms of its standards.
Okay, thank you, John. Brian, Valerio, want to add anything to John's reply?
Just to say, because we mentioned outdoor versus indoor in the slides for the PAS, I think the idea was that it was solely focusing on outdoor, not particularly because sensors are better suited. At the time there was a larger body of work on and knowledge on outdoor use, but obviously the context is slightly different. So concentrate, as John said, the pollutants themselves can be different. The levels can be different. So you obviously very enclosed environments, you get really large concentrations, and environmental conditions as well. So you could go from high humidity to a smaller temperature range. And whatnot. So it's slightly different context, but it is a very, very strong area for sensors. Yeah.
Okay, thank you. Gonzalo Rosado is asking, in line with what has been mentioned and with the methodologies used to assess the performance of low-cost sensors, to what extent can the incorporation of statistical techniques, such as those using machine learning or the use of AI, be considered appropriate or inappropriate for data processing prior to performance testing? I don't know who wants to take on that.
Nobody.
No, I'll answer that one.
Okay, go on, John.
Yeah. I mean, basically, at AlphaSense, we made low-cost sensors, and I'm frustrated over ML and AI being used before you apply your straightforward chemistry and physics that you should apply to a sensor, like baseline, something like first-order reactions, stuff like. I have no problem with ML and AI to categorize readings after you've done your chemistry and your physics. If you do that first and take care of baseline errors and things like that, which is common good sense among scientists, then ML and AI are totally useful. But before then, it's not the brightest idea.
Absolutely.
Brian?
Yeah, no, I completely agree. As metrologists, I think we all get a little bit nervous about arbitrarily applying AI or machine learning to the data that we have. We really want to be confident that what's being measured is what we want to be measured.
Yeah, absolutely.
Valerio?
And can I just add, I think I agree. I think the key in that question is the prior, that's a bit concerning. Before, yeah, I absolutely agree with John. Even for the, say, corrections you might want to implement after your deployment and your initial corrections based, say, on physics or chemistry. We've done some work, the graduate student did some work on this, and ML or AI doesn't necessarily outperform some less sophisticated, if you will, regression techniques. So it's balancing. Yeah, it's not the cure of it all, in and of it all, I think.
Yeah. I think the most useful time I've seen ML and AI used is when you're doing across platforms of point sources with low-cost sensors plus satellite, plus some sort of modeling. There you might have ML and AI being useful. But on a single point source, be very, very careful.
And just to add to that, there is the issue about transparency and traceability of methods, reproducibility. So that's quite a rabbit hole.
17660, we argued at 17660 over the problems that manufacturers don't want to tell us their secret sauce, but we want transparency, and how to cross that barrier between making sure the data they see is honest, as well as and that one, Brian, what do you think about that one?
Yes.
Okay, that's good.
I'm just trying to work out how I wanted to respond. I mean, I think the challenge is making sure that what the sensor claims to measure is actually what it is measuring, and there are very, very clearly highlighted challenges around claiming to measure, for example, benzene, where in fact what you're actually measuring is carbon monoxide. So it's really important that the test processes pick up on that kind of anomaly.
Okay, thank you. We have 3 more minutes, so I will go with the next question. This comes from Samara Carbone. She is part of our steering committee. So the question is there a recommendation about intercomparison, collocation frequency related to low-cost sensors, long-term measurements? That is there a recommendation on how often it should be done? ISO or another standard, she asked.
The answer is no.
I think, yeah, there's no consensus, is there? I think the PAS provides a figure. I can't remember now. I should know this. I think it's to account for that seasonality effect. I think the recommendation is either 3 or 4 months. But obviously, that's depending if you're dealing with large numbers of sensor systems deployed over a network. That becomes really intensive in terms of the workload.
And that was one of the real catch points over how often you should do these tests when we were discussing and building the standards. You know, do you do it every 3 months? And the answer is probably yes. Do you do it in environments where you capture all of the variability in the temperature and humidity and particle composition, for example, where that changes, where for example, in Nordic countries where your composition changes radically in the winter. And the answer to all that is, yeah, you really need to understand that, but it becomes prohibitively expensive. So you have to kind of apply some pragmatism to the approach that you take, unfortunately. So the answer was, as John said at the beginning, no.
There's a couple of useful comments. One is that we deal with 3 seasons, not 4. Spring and autumn are effectively the same. Okay, temperature, humidity are changing all the time. Winter and summer are, one's hot, one's very cold. It turns out that most of these sensors love winter because the temperature is really low, all the zero currents disappear. It's wonderful. And we hate hot summers, but it's the transients that cause the trouble. So if you try to calibrate during a period when the temperatures and humidities are changing rapidly, and September or April, you're going to have trouble moving that. There's some very good work that the guys at MIT did on seasonal dependence of the sensors. Also, it depends on what you're measuring. NO2, ozone are very difficult to measure. They're very reactive, whereas carbon monoxide and hydrogen sulfide sensors are incredibly stable over time. So it kind of depends on the sensor. And also the optical sensors used for PM tend to be more stable than the chemical sensors used to measure the gases. And that's quite an important point, actually.
Okay, we have still a number of questions. I will submit these questions to our presenters and see if we can reply one by one those questions. Again, to the attendees, to our speakers, thank you very much for joining. It is wonderful to see such an interest. We will, just for you all to know, we will continue with this series of webinars. We will also try to go deeper into the standardization world. Our aim is to have voices from Asia, from Africa, from the US, for example, to see how people is doing that sort of activity. So thank you very much and see you on the next webinar, hopefully. Take care.
Thank you, everyone.
Thanks, everyone.
Thank you very much.